Hey guys, and welcome back. So here we have an HP laptop for repair today. So this is a no power case, so it doesn't turn on. So let's see whether we can fix this today for the customer. Okay, so look at the ampere reading on the DC power supply. Now I'm connecting the adapter. So yes, so you can see 11 milliamps, yes, 200 milliamps. I think the battery is charging. Yes, 1.2 ampere. And you can see on this side we have orange LED, so the battery is charging fine. Okay, so if I open the laptop, so here we have the Intel i5 processor, which is 4th or 5th gen, I think. Okay, so if I press the power button, yes, now the charging has stopped. Okay, again it starts charging. So when I press the power button, the charging is interrupted and again it's charging. Yes, but the board is not turning on. Okay, so when I press the power button, the board is not turning on. Okay, now let me just disconnect the battery so we can just have only the ampere reading that the board is drawing. Okay, so this may confuse us, so I'll just disconnect the battery and connect the adapter to find out the current reading by the board. Okay, so now it is around 1 milliamps. Yes, so if I press the power button, I'm getting 12 milliamps or 13 milliamps. So there's a change in the ampere reading when I press the power button. So when you're dealing with the no power case, so we can first go to SIO, the EC chip, and then we can check all its requirements, and then we can move forward to PCH. So because EC chip is the controller IC that receives the power button or power input signal, then only the EC chip will inform to the PCH. So first our checkpoint for no power is the EC chip. So when you press the power button, you can see there's some improvement. So there's a change in the ampere reading. So we can confirm that the EC chip is trying to do something when we press the power button. So on that case, we can confirm that the EC chip is partially working to do something. Anyhow, the actual problem can be seen only when we diagnose the motherboard. Okay, so now what I will do, I will just remove the laptop and take out the motherboard, then we can diagnose it properly. First we can start from the EC chip, then we can move forward to the PCH and its sections. Okay, we need to check the requirements of all the sections in the SIO first, then we can move forward to the PCH. Okay, now we have taken out the board and it looks so dusty, so I'll just clean it. Okay, so now we can have a visual check on this board here. So if anything is visible, we can immediately spot that. So it looks fine, I think, on this side here. Yes. So nothing much on this side. On the other side, so here we have so many components, so we can look this way. Okay, everything looks fine, I think. So there's no problem, so nothing is visible. Yes, so everything is fine. Okay, now let me connect the adapter again and see if there's any improvement after cleaning the dust, just in case. Okay, it is drawing 8 milliamps, so pressing the power button, so it is now 10 milliamps and there's no change on the ampere reading and it is same as before. Okay, so now we can start our basic check from the EC chip here. So we can start our basic check from the EC chip. Then we can move forward to the PCH, which is the SOC here. So before that, I will just check the diode value of all the inductors here, just in case if there's any short directly on the inductors. Negative probe on the main power rail, checking all inductors. 500, yes. Yeah, it's good. Checking the ground, checking the load towards the ground. Yes, that is fine. Yes, good. Yes, this one here. Okay, everything looks perfect. So there's no short directly on the inductors here. Right. So let's focus on the EC chip here. So when we press the power button, the EC chip is trying to do something. So we are getting a different changes, or we are getting a change on the ampere reading. So the EC chip is trying to do something when we press the power button, but something is hindering the EC chip to move further. Okay. So let us check our basic requirements for the EC chip in order to release all of its signals like RSM reset, power button output signal, then the PCH power enabled signal and things like that. Okay, so basically we can check the RSM reset on pin number 100 usually if it is a KB9012 or KB9022. So this one here we have KB9022. So it is same. So we can check on pin number 100 to see whether we have the RSM reset, which is the resume reset signal for the board to turn on. So if the RSM reset is 0, your board will not turn on forever. Okay, either before or after pressing the power button, we should have 3.3 volt on the RSM reset pin of this EC chip. So we can check it on pin number 100 here. Yes. Turning to voltage mode and pressing the power button, and we don't have any voltage. Let me check once again. Yes, on pin number 100. Okay, pressing the power button, turning to ohms value. Yes, so 49 ohms is a low impedance, so the EC chip is sending a low impedance on this point, so the RSM reset is actually low. So if RSM reset is low, your board won't turn on because the PCH will see the RSM reset signal whether it is high or low before releasing the S4 and S3 signal. So most importantly, if the BIOS inside the EC chip is not good or if it is corrupted, then the RSM reset will be 0. But I am sure the BIOS inside the EC chip is okay, the firmware is good, because we are having a white light on the DC jack here and the EC chip is charging the battery, so it is working fine. So the firmware of the EC chip is good. Okay, so what can I do now? So we are in a situation to open the schematics. So here comes the importance of the schematics. So we can just look at the requirements for the EC chip and what are the signals and what are the voltages that needs to be present for the EC chip to release the RSM reset to high. Okay, so now let me refer to a schematic. So the board part number is here. I'll just try to find a schematic, so which is LA-C701P. Okay, I'll just try to find the schematics and come back with the checkpoints. Okay, so this is the schematics of this motherboard. So before moving down to the EC chip to check its requirements, first we need to go through the schematics and try to find if there's any treasures in these schematics here. So do you know what I mean treasures? So that is the power on sequence in the schematics. So not all schematics has this power on sequence chart, But if we have it here, then it will be very helpful for us to find the fault in this motherboard. So basically you will find two types of power on sequence chart. One is based on the timeline and the other is based on the sequential order which the signal should be generated. Okay. Okay, so let's move down and try to find through the schematics whether we have those power on sequence chart in the schematics. Okay, so this is the block diagram, and the power on sequence based on the timeline will be available mostly within the first pages of the schematics, and if we don't have it there, mostly we will not have anywhere on that schematics. Okay, I think we don't have it here. So moving down, let's see whether we have the other power sequence chart. Yes, so here we have the power on sequence based on the signals that is generated one after the other. So you can see here each of the signals are numbered and they are in a sequential order, and it should be present in an order for the motherboard to turn on and give display. Okay, so if you look at the first signal, that is the on-off signal to this block here. So this is the KBC, which is the EC chip on this motherboard. So EC chip is the only controller that receives the on-off signal as an input from the power button directly. And once it receives the signal, it will send a signal called the EC on signal to the standby IC to release the 5 volt and 3 volt inductor voltages. And on the third sequence, it will send a signal called PCH D power OK, which is deep sleep well power OK, inside the PCH. So we have the PCH here and the CPU on this side. So this is integrated together, and we call it as SoC, system on single chip. So if you look here, the first sequence is the on-off signal, and the second sequence is the EC on, and the third sequence is the D power OK, and then only it is sending the power button output signal to the PCH. So we have two signals in between the power button output and on-off signal. So this is because the EC on signal goes to the standby IC to release 5 volt and 3 volt inductor voltages. And these two inductor voltages are mainly for the purpose of deep sleep well power for the PCH, which is the suspend power for the PCH. So this voltage will go straightly into the PCH as the suspend power. And this is the purpose of generating this voltage before all of these signals here, which is the SLPS5 and SLPS3 signal. So these voltage should go inside the PCH in order to release this signal. So the suspend power should be active for the PCH to release these S4 and S3 signal, or S5 and S3 signal. And once the EC chip sending the signal, which is the power button output signal, to the PCH, then the PCH will send another signal called PM_SLP_ sus signal. So this will turn on the suspend power for the PCH. With regard to this signal, it will send a signal called, which is the EC chip will send a signal called PCH power enable signal. This signal will go straightly into a switch, and that switch will switch 3 volt always as 3 volt PCH, and this will go straightly to the PCH deep sleep well power as a suspend power for the PCH. And then on the 7th sequence, the EC chip will send PCH_RSM RSS signal to the PCH. So this is informing the PCH to wake up the system or to resume the system from the deep sleep. And once it sends the signal, the PCH for the last time it will send a signal called sus warn signal. This is to confirm or to receive the confirmation from the EC chip that all the suspend power for the PCH is okay and stable, such as the deep sleep well power, the EC on signal, PCH power enable signal, and D power OK signal. Are they all okay? Just as a confirmation by the PCH. And if everything is okay, then the EC chip will send the sus acknowledgement signal as a confirmation for the PCH that all of them are okay, all the suspend powers are okay. now you can release the S4 and S3 signal to wake up the system from the deep sleep. And then only the PCH will release this signal, which is the S5 signal and S3 signal. So the S5 signal or the S4 signal, either one will be used. So here they are using S5 signal, so that is fine. So this signal on the sequence 10 will be sent to the EC chip, and based on this signal it will release another signal as system on signal on the 11th sequence, and this signal will go to the RAM regulator to generate 1.35 volt, and on the 12th sequence the PCH will send another signal called the S3 signal, and once the EC chip receives this signal it will send another signal called SUSP hash signal. So this signal will turn on all the run power voltages in this motherboard. It will go to the RAM regulator to generate the RAM termination voltage, which is half of the RAM voltage, 0.675 volt. And also it will go to all the load switches such as 5 volt and 3 volt run power load switches. This will generate 5 volt and 3 volt always as 5 volt and 3 volt run power. And also another voltages like 1.5 volt for UMA and 1.5 volt for discrete. If it is a dedicated graphics, so 1.5 volt will be generated, and if it is an integrated graphics, another 1.5 volt will be generated. And also it will go straightly into this regulator here to generate 1.05 volt as a power for the PCH main power. And on the 14th sequence the EC chip will send the keyboard reset signal, and on the 15th sequence the EC chip will receive the power good signal from 1.05 volt regulator, and with regard to this signal the EC chip will send another signal called EC 1.05 volt power good to the PCH to inform that the PCH power is OK. And on the 17th sequence it will send the PCH power OK signal with respect to this signal here. So this will be sent first and this will be sent second. After the PCH receives these two signals, which is 1.05 volt and PCH power OK, then the PCH will inform the CPU that all of their powers are OK except the core. Then the CPU itself will turn on the CPU power on the 18th sequence. So this VR on signal will go into the V-core regulator, and that regulator will generate the voltage for the CPU. And on the 19th sequence the V-core regulator will generate a power good signal called V-gate, confirming that the CPU power are also OK. And on the 20th sequence the EC chip will send another signal called system power OK. So system power OK includes the power of the CPU as well. So all the system's power are OK, including the CPU power. And after CPU receiving this signal, or the PCH receiving this signal, then the PCH will release the PL2 reset signal on the 21st sequence. So this is the last signal that is released by the PCH, which is the platform reset. So entire reset for the whole platform, that is the PL2 reset, and based on that the CPU will officially start to work its first operation. So this is how the power on sequence goes through the motherboard. So let us check one by one these signals and find where would be the fault in this motherboard. Okay, so we can start checking again the EC chip requirements. So we can leave the on off button and also the EC on signal, because the EC on signal is there, that's why we are getting the 5 volt and 3 volt inductor voltages. So we can leave those two signals, but we can check the deep power OK signal from the EC chip. So deep power OK is on pin number 127. Yes, pin number 127 is here on this point. Yes. Okay, if I press the power button I'm getting 3.3 volt. So deep power OK is sent by the EC chip to the PCH. So third sequence is fine. Let's move on to other one. The fourth one is the power button output signal from the EC chip to the PCH. Yes, so the power button output is on pin number 122. Yes, this is 120, 21 and 22. Okay, and we don't have any voltage there right now. And if I press the power button, yes, I'm getting 3.3 volt. So that is also working fine. So the EC chip is sending 3.3 volt after pressing the power button. Yes. And when I press the power button, also I'm getting a response on the power button output. So it is receiving the power button input and sending the power button output as high to low, then to high. And that's why I'm getting a fluctuation on the multimeter when I press the power button. Okay, so now the fifth sequence is PM underscore SLP underscore sus hash signal from the PCH to the EC chip. Okay, we can find that. So that is on pin number 16, which is PM underscore SLP underscore sus hash signal. So 5, 10, 15 and 16. Okay. And if I press the power button, I'm getting nothing. Yeah. Sorry, I didn't connect the adapter. Okay. Pressing the power button and nothing. If I turn to ohms mode, and you can see it is 47 ohms. So the PCH is not sending the sus power on signal to the EC chip to turn on the suspend power for the PCH. So now if I check the voltage on the PCH power enable pin on this EC chip here, and we won't find any voltage because that voltage is generated based on the input voltage from pin number 16 of the EC chip here. Yes, so PCH power enable signal is on pin number 107. I'm sure we will not have any voltage there. Anyhow, we will check it. So this is 100 here. 1, 2, 3, 4, 5, 6, 7. Yes, this one. And if you look here, we have 17 ohms. That means we have low impedance on that point. If I press the power button, no response, just it is 18 ohms. So no response, just it is 18 ohms. Okay. So I think we need to check the requirements for the PCH right now, because up to PCH deep power okay, the EC chip is working fine. But we are getting a low impedance on PCH power enable because the PCH is not sending a high logic on the PM underscore SLP underscore sus hash signal. So that's why we are getting 0 volt on the PCH power enable, and hereafter no voltage or no signals will be there in the power sequence, because here we have a break on the PCH on the signal called sus hash signal from the PCH. So we need to find why the PCH is not releasing that sus hash signal as high. Then only the power sequence will continue thereafter. Okay, now we will move on to the PCH and find there would be the problem. Okay, so now we are having a problem on this point here on the fifth sequence. So the PCH is not releasing these signals as high in order for the EC chip to release a high logic on this point here as a sixth sequence. So if you look at this signal here, so this is a part of power management of the PCH. So this signal comes from the power management of the PCH. And if there is a problem with the power management inside the PCH, or if any requirements are not met, and this signal may not go high in order to release the suspend power for the PCH. So when it comes to the power management, first we need to focus on the real-time clock of the PCH, which is the RTC, and also the 32 kilohertz crystal on this motherboard here, and it should be oscillating 24/7. So we need to check that and see if there's any problem with that. First we will focus on the RTC section, and then we can move forward. Okay, so this is the RTC section of the PCH, and this is very crucial to check if you're having a no power problem. And on this side here we have two important signal called PCH SRTC reset and PCH RTC reset, and you should have always 3.3 volt on these two signal 24/7. So if there's any voltage drop on these two pins, then at that time your time and date will be lost. And when you are turning on the motherboard, you should have 3.3 volt on these two signals, then only your motherboard will turn on, otherwise it will not turn on. Okay, so we need to check whether we have 3.3 volt on these two signals, and these two signals are given to the PCA through a pull-up resistors, and those resistors may open or may expand its values. Mostly these resistors will be in 20k 20 kilo ohm resistors, and it should be appropriate. Okay, so we can check the pull-up resistors for these two signals here. Okay, yes, so here we have it. So 20k for both RTC and SRTC reset, and here we have the jumper pad for CMOS reset. So if you want to reset the BIOS, or if you want to raise the time and date, you can just short this to ground and your old CMOS information will be erased. And sometimes if you are having a no power problem, if you are resetting the CMOS, your board may turn on, so we usually do that. Okay, so if you are having a problem on these resistors here, on these two resistors, we need a board view to find this resistor. So if you don't have a board view, then it will be very challenging to find it, but we have a trick to find it. So what I usually do is, so I just disconnect the adapter and I just connect the CMOS battery in the motherboard, and I just continue checking the voltage on every resistor surrounding the CPU, and on some of the resistors you will find 3.3 volt, and if you find the resistance value approximately around 20k, then that is your SRTC and RTC reset. So by doing this trick you can easily find the resistors, but if you have this board view, then it will be easy to find those resistors. So here also we don't have the board view, so we are going to do the same method. Okay, before checking this one, I'm going to check the crystal on this motherboard here, which is the 32.768 kHz crystal, and this crystal should be oscillating this frequency 24/7. And if there's any drop in the frequency, then your time and date will be raised and the BIOS will be reset and it will be in a default mode. And also if when you are turning on the motherboard, if it is missing, this frequency is missing, then your motherboard won't turn on. So now we can use our oscilloscope to check whether we have this frequency on this crystal here. Okay, then we can move forward. Okay, so the 32 kHz crystal is under the heatsink, so I'll just remove it. Okay, and it's here. Okay, so something is visible on the 32 kHz crystal. If you look at that, we have a green color mark surrounding the crystal there, and it looks like some water moisture damage. I don't know. Okay, so let me check whether we have 32.768 kHz crystal there. I mean the frequency there. Connecting the adapter. I think we don't need the adapter. We have the CMOS battery in this motherboard. So the frequency should be there if we have a CMOS battery on this motherboard here. So let me check the voltage on the CMOS battery. Yes, we have 3.3 volts, so that is fine. Okay, checking the crystal here. So look at the oscilloscope. Okay, set to auto mode. So if you look at the oscilloscope, so we have some reading there. So the voltage is there, but there's no frequency. So that confirms that the SRTC and RTC reset is okay, but the problem is actually with the crystal here. So let me try to replace a new crystal here and see whether the board is turning on. Okay. Okay, so here I have a scrap motherboard with me, so I can use this crystal here. First I will see whether this crystal is okay. So I can use this CMOS battery in this motherboard here and check whether we are getting 32.768 kHz crystal frequency on this crystal here. Okay. Here we have the crystal. So if you look at on the oscilloscope, we are having approximately around 32.768 kilohertz frequency. Yes, so that is clear, and so you can see the waveform that is very clear. Okay, so now we can try to replace this crystal on this motherboard here. Okay, so now I have replaced it. So let me check whether we have the 32.768 frequency now in this motherboard. So look at the oscilloscope. Okay, probing on this point, and yes, we have 32.768 kilohertz frequency. So that is working fine. So on this side, yes, so both of them are okay. Wow. So let me connect the adapter and see whether the board is turning on, and we can again check the requirements based on the power sequence and see whether this time we are getting the PM_SLP_sus signal and also the RSM reset signal, and see whether the board is turning on. So if the board turned on, then we can confirm that every requirements are met, including the RTC here. Okay, look at the ampere reading. Now I'm going to connect the adapter. Alright, so ampere reading 8 milliamps, and pressing the power, and yes, the board has turned on. Now it is drawing around 400 milliamps. So let me try to connect a mouse and see whether we are getting a display. So look at the importance of the RTC crystal here. So it should be oscillating correctly for your motherboard to turn on. Okay, right. So the board has turned off. So let me press it again. Yes. And we got the display. So everything is working fine. So I'll just assemble inside the laptop and let's go for a last check. Before that, we can check the requirements of the EC chip once again. We can just check whether we are getting the SLP PM_SLP_sus signal this time. So now I didn't press the power button, and you can see the ampere reading is around 1 milliamp on pin number 16. So 5, 10, 15 and 16 is on this point here. Yes. So before pressing the power button, we have 0 volt. You can see here we have 0 volt, and if I press the power button, and I'm getting 3.3 volt. So now the RTC section is proper, so that's why the power management is now active, and it is releasing the sus signal to high. Okay, I think all the signals are okay, because now we are getting the display executed by this motherboard. Okay, so everything is assembled inside the laptop. So let me try to press the power button and see whether we are getting a display. So connecting the adapter. So battery is charging now. Okay, then it stopped. Yes, so 1.3 ampere. Pressing the power button, and yes, we have response, and it has turned on, and now the battery has started charging again. So everything is fine, and we got the display. So Windows is booting, so everything is working fine. Okay, so I'm happy that I was able to fix this laptop here. So thanks for watching, guys, and stay tuned for our latest update, and see you later in a new video. Okay.